Hi class, Ms. Cornacchione here to talk to you today about our new unit called Fields. And this video is on topic C1, which is the Introduction to Fields and Newtonian Gravitation and Orbits. So this cartoon here is Sir Isaac Newton, who is a famous physicist and mathematician. And the story goes that he was sitting under an apple tree contemplating the mysteries of the universe, and suddenly an apple fell from the tree and hit him on the head. And that was the aha moment that was key for the development of his understanding of the force of gravity. And historians have really dug deep to find evidence that there really was an apple tree and an apple falling from it, but it might not have actually hit him in the head like the cartoons and jokes suggest. This is a relevant story to tell you now. It is April 2020 for this video, because around the time of Sir Isaac Newton's apple tree story, Newton was a college student and he was told to stay home from school to prevent the spread of the Great Plague of London. Sound familiar? I guess my point is that though there's a lot of bad news in the state of the world right now, perhaps the time spent at home will provide just the right environment for inspiring, brilliant ideas, creative writing or art, breathtaking music composed. So we're just all trying to figure out how to use our time wisely, the best that we can given our circumstances. Remember that in grade 11 and previously in this course, we've learned about different types of forces: applied force, friction, tension, normal force, air resistance, spring force. And these are all contact forces. You also know of at least one non-contact force, which is a force at a distance. So we have gravitational force that you should be aware of. There's also electric force and magnetic force, and these three forces are the forces that is the focus of this field unit. So if you visualize, you have one horseshoe magnet. When you hold it even near another horseshoe magnet, they don't actually have to touch for you to feel the attractive or repulsive forces. So that's what we mean at action at a distance. When you hold an object at some height above Earth's surface, the object doesn't actually have to touch Earth in order to feel the attractive pull of the Earth. And so what are force fields again? So a force field is found in the space surrounding a magnet or surrounding the Earth in which that force can be detected. So all non-contact forces have a force field, which is like a map that describes the force experienced by an object placed at different positions. For example, this is a slide from my grade 11 slides, if we had grade 11 together. So the gravitational force field is mapping out the direction and strength of the force of gravity experienced on another object with mass placed within this region. And the Earth is surrounded by this gravitational force field. And the arrows of the lines tell us the direction of the force. So notice the direction of the force of gravity is always towards the center of the planet. And the strength of the force depends on how close you are to the Earth, because the strength is indicated by the density of lines. So you can see if you're close to the Earth, the lines are more dense, the force is stronger, and if you're further away, the force is weaker. And you might wonder how we know the fields exist. So there's different ways to observe them. And simply for magnetic fields, just sprinkling iron filings around a magnet, you can visualize these lines. So we know that there's a region around a magnet, a three-dimensional region around a magnet where there is an attractive force. So this is the fields unit. So we're going to be talking about multiple fields, force fields, but they all have in common, whether we're talking about magnetic, gravitational, or electric force fields, that these fields are three-dimensional. And we can model these fields using the field lines. The field lines do not cross. The concentration of the field lines indicates the strength of the field in that region, so the concentration of the field lines. And then the field lines indicate direction of the force. So there's always an arrow on those lines. In chapter 6, we're going to focus on gravitational fields. So an object with mass will create a gravitational field in the space surrounding it. And that force acting on a second object with mass will always be attractive. In chapter 7, we're going to talk about electric fields. A charged object will create an electric field in the space surrounding it. And that force acting on a second charge, also a charged object, a second object, also a charged object, may be attractive or repulsive. And then magnetic fields in chapter 8, a magnet will create a magnetic field in the space surrounding it. And that force acting on the second object may be attractive or repulsive, depending on if it's a north or south magnet approaching this field. So you can already see there are some similarities and differences, which we're going to highlight throughout the unit. But for now, we're in the first chapter of this unit, and we're going to focus on gravitational fields, and specifically in this lesson, celestial mechanics. So our goal is to extend what we know about forces and energy out into space. And we'll be focusing right now on gravitational potential energy in space. If you recall, about a year ago as of this date of this video, so April 2019, it was all over the news that there was a team of astronomers that captured the first picture of a black hole. And although seeing this blurry photo might seem underwhelming at first, but it's actually a really big deal. So before this photo, Einstein's theory of general relativity was used to predict how the black hole would look, and the real photo looks close to the prediction. This increases our confidence in Einstein's theory of general relativity, which is an area of science that experiments are difficult, if not impossible, and data is slow to come by. And just overall, this result contributes to understanding of the universe. So it is actually a really big deal. And it took a lot of time to create that image. And there's lots of resources out there if you're interested in learning more about that. So for the examples that we're about to go through and the equations that we're about to do, these are the learning goals. So you should be able to explain quantitatively and qualitatively the strength of the gravitational field, understand what characteristics are required in order for an object within a field to experience a force, be able to determine the value of this force, and differentiate between weight and mass. Some of these learning goals we've been working on for a while. Okay, so celestial mechanics involves the calculation of the motions of celestial objects such as planets. And this motion is a result of the gravitational fields in space. Since we don't know the gravitational field strength at every location in space, we need a better way to determine the force of gravity. So we come to Newton's universal law of gravitation. There is a gravitational force of attraction between any two objects with mass m1 and m2, and their centers are separated by distance r. The magnitude of the gravitational force on either object is directly proportional to the product of m1 and m2 and inversely proportional to the square root of r. So this proportionality can be written as a mathematical statement, Fg equals gmm over r squared. And g is not like the lowercase g that we used so far in this course, in last year's course, 9.81 meters per second squared. If we take a look at this constant, how to get from kilograms squared divided by meters squared to newtons, The units are newtons meters squared per kilogram squared, and that's just whatever newtons need to be so that the unit analysis works out to be newtons. And the value, which was determined experimentally, is 6.67 times 10 to the minus 11. And that's called the gravitational constant. It's called the universal gravitational constant because unlike 9.81, which is only applicable at the surface of the Earth and only for the Earth, the universal gravitational constant is universal, so we can use it anywhere in space. M1 and M2 are the masses of the two objects. R is the distance between the center of the two objects. I'm just going to flag this right now, and I'll say this a few times right here, this R. So you think of R, you think of radius, but this is the center to center distance. And it's a common mistake to accidentally just substitute in the radius of the planet, which is only, or just the altitude that's given in the question. You can only sub in the radius of the planet if you are extremely close to the surface of the Earth. Now that we're in grade 12, just as a warning, we're probably not going to do the problems in this chapter where you can just sub in 9.81 times your mass. So always check if the altitude is significant, and most often it is. So you have to do the altitude plus the radius of the planet to get this R, center to center distance. So that's one tricky thing. So you might be saying, we already have an equation for a force of gravity, Fg. From last year, we had Fg equals mg. So what's going on here? Is this different from Newton's law of gravitation? Well, it's actually just, we didn't lie to you in grade 11, but this is just a very simplified form of GMM over R squared. So let's take a look at what I mean by that. So first of all, when I write this, we're usually talking about one mass being much bigger than the other. So I usually use capital M for the first M. And many times it is Earth. If we're talking about comparing this to the equation we learned last year, we would be talking about M1 being the mass of the Earth. And if we're talking about problems from last year, we had R basically being the radius of the Earth. We weren't talking about very high altitudes, or we just simplified it to be the radius of the Earth. So it actually would look like this, and the GM over R squared, this is all could be bundled into a constant. So we've got a constant times a constant divided by a constant squared. Instead of us always looking up those numbers and writing them all out, they've been bulked together to be small g, 9.81, if we're talking about the mass of the Earth and the radius of the Earth. So this equation here, we weren't lying to you in grade 11. We just simplified it by bulking these constants into this number 9.81. It's only valid near the surface of the Earth. 9.81 can only be valid at the surface of the Earth. We could use this equation if we were given small g of the moon, the gravitational field strength of the moon. We could have used this equation there. But we will be focusing on using this equation either for the Earth or for another planet. So just seeing this visually, so we already knew that the rock was experiencing an attractive downwards force, downwards towards the Earth. So that's what we already knew and was intuitive because we see it all the time. What might not have been obvious until you read this chapter on Newton's universal law of gravitation is that the Earth, there's an equal force pulling the Earth towards the rock. So this is an action-reaction pair according to Newton's third law. So from a grade 11, if the rock mass, so why was this force so much more noticeable than this force? So think about it. We were talking about a relatively small object being pulled towards the Earth. So M1 was much smaller than M2. This year we know if we have M1 and M2, we have G, we have to know the center to center radius. So, okay, why was this force much more noticeable in our grade 11 problems. So if the rock is much smaller than the Earth, we only see the rock falling towards the Earth because the amount of force has a big effect on a small mass, but essentially no effect on the mass of Earth. So recall, according to Newton's second law, for a set force, so this force is equal to this one, mass is inversely proportional to acceleration. So this is a really big mass, so it'll have a very small acceleration, or like barely anything at all. For a small object. For a small mass, it'll have a really big object because MA here has to equal MA here. So I hope that makes sense. So the universal gravitation gives us a few facts. It gives us that the relationship between force and distance is inverse squared relationship. So as the force, let's say if R was increasing, like doubling. So if we double the distance, 1/2 squared was actually 4 times. So 4 times smaller. So if we double the distance, the force is 4 times smaller. Newton's third law applies. For every action force, there is an equal and opposite reaction force. So in this case, the attractive force M1 has on M2 is equal in magnitude, but opposite in direction to the attractive force of M2 exerting on M1. So we can write this mathematical statement of Newton's third law. For the gravitational force to be noticeable, at least one of the objects must have a large mass relative to the distance between the masses. And when one of the masses is Earth and the other object is near Earth's surface, the equation simplifies to Fg equals mg. So if we notice, if we analyze this data, we've analyzed this data before in grade 11 to say, oh, okay, as altitude increases, the gravitational field strength decreases. And that just supports that inverse square relationship between the force and the distance. Okay, let's try an example using our new equation for Fg. Terence has a mass of 67.8 kilograms and is standing on the surface of the Earth with a mass of 5.9742 times 10 to the 23 kilograms and a radius of 6.378 times 10 to the 6 meters. Calculate the force of gravity Terence experiences. 2 ways. Okay, well, in one way, we would need to know the gravitational field strength and do Fg equals mg. We can still use that if we do know small g. Right now, the go-to way, we've got a radius and 2 masses. What might pop into your head right after doing that new equation is to use the new equation. So let's draw a diagram. We've got the Earth, which is much more, we are talking about the Earth. Okay, so the mass of the Earth, the mass of the person, and that distance. So calculate the force of gravity. So we do have small g because we are talking about the Earth and we're on the surface of the Earth. But let's try it both ways just to see if what I was saying makes sense. GMM over R squared, we substitute in this new constant. So it's, I mean, if nothing else, doing all the practice problems is really important because then you get used to these constants that have maybe values that we're not familiar with and units that we're not familiar with. So we substitute in the values, do a little unit analysis, and we get 664 newtons. Note that if we solve this problem using mg, we also get 664 newtons. And the reason is because if you try it, if you don't believe me on your calculator, gm over r squared in the case of Earth gives you 9.81. So either way, we get 664 newtons. And if we just check, we've got 3 significant figures in our smallest number of significant figures. I apologize, my cat has just come to join us. She's really enjoying physics these days. Her breathing's probably audible, but she's really cute, so I can't take her away. So let's compare. We used Fg equals mg and Fg equals gmm over r squared. Let's compare. Mg, we can only use that near Earth surface. little g is 9.81 meters per second squared, or when g is known. It's simpler, but we can only use it when g is known. The other equation, our new universal equation, it can be applied to all objects in space. It's a little bit more math. I guess if we had to solve for something other than, if we had to solve for the center to center distance, we can't use that at all. So this is a little bit more complicated, but it's the only option. So using the formulas together, if we set mg, like m small g, equal to big G mm over r squared, we can cancel out the smaller of the m's, and we're left with that the gravitational field strength is big G, big M over r squared. So big M is referring to the mass of the planet, or the bigger of the two masses. So we've got the gravitational field strength is the amount of attractive force in newtons that a unit of mass would experience at a point in space. So this is our equation. And consider this. So we've got a list of all the planets and the gravitational field strength at the surface of those planets. So what could we conclude about these celestial bodies? Justify your response. So is it that they all have less mass? Is it that, because the FG, is it that they have less mass? Let's go back. So how could this be smaller? Is it that they all have less mass? The other way that G could be smaller is if the denominator is bigger. So less mass or larger in radius? So the truth is that it's just a combination of the mass over r squared being smaller than Earth. So basically, if you could stand on the surface of any planet, you can't because some of them are gases, but if you could stand on each planet, you would feel lighter than you do on Earth. And it doesn't matter which planet you were standing on. So let's do one more example. Oh no, sorry, just kidding. Example 2, Eris, a dwarf planet, has a radius of 1,200 kilometers. If an astronaut stands on Eris, he drops a rock from a height of 0.3 meters, and this takes 0.87 seconds. What is the value of G on this planet? Calculate the mass of Eris. So a bit different than example 1. So for a height of 0.3 meters, this is our displacement. Our time is 0.87 seconds. Our initial velocity is 0. We're really solving for, when we solve for small g, we're solving for the acceleration due to gravity. So the kinematic equations, equation number 3 is going to come in handy here. We isolate for A. We sub in our numbers, which the numbers that matter are height and the time to the bottom. And that gives us our G value of 0.79 meters per second squared down. Calculate the mass of Eris. Now that we know small g, we can find the planet mass by isolating big M, substituting in our numbers, and solving for M, and we get 1.7 times 10 to the 22 kilograms. Just a note here, one thing that makes the equations in this unit are pretty simple. It's not too bad. It's not like our conservation of momentum and energy system of equations problems. The math is simpler, but why can there be just as many mistakes? When you do your common sense checks, you don't have as much background with the mass of planets or the radius of planets. So the more problems you do, the more you'll be able to say, yeah, 10 to the 22, that does sound like the mass of a planet. And our constants are also, we've got so many scientific numbers that are expressed in scientific notation because we are talking about numbers that are very small and very big. So you really have to know how to use scientific notation on your calculator. And I know that you've probably already done that for years, but if you are not using the EXP button or the EE button, it's time to learn, and it's time to really take advantage of those functions on your calculator. Unit analysis is another tool that's going to help you. So common sense checks for the order of magnitude, unit analysis for your units, and knowing how to use your EXP and EE buttons. Those are keys to success in this chapter. Oh, okay, we have another example. So we've got 3 asteroids in space that are shown in the diagram below, and they all have the following masses. So 1 times 10 to the 20, 2 times 10 to the 20, 4 times 10 to the 20 kilograms. Determine the net force on asteroid A from asteroids B and C. So asteroid A is going to be influenced by this as well as this. So how would we do those problems? We have to do the sum of the forces. So let's start with the free body diagram on A. So A has the force of C on A, that's attractive and to the right. There's the force of B on A, that is attractive and up. So we've got over and up. We know that the net force will be somewhere on a diagonal, but to find the magnitude and the specific direction, we're going to need to use universal laws of gravitation. So we substitute in for Fc on A, we would sub in the mass of C and the mass of A, and then the center to center distance, we need to know these center to center distances over here. So RAC is 2.5 times 10 to the 10 meters, so we sub that in here. And that's FC on A. That's pointing in this direction. So we've got that. Let's not round it yet. Then we do the same for FB on A. So this object is going to be pulled upwards as well as pulled over. So we've got an upwards force. Now, the diagram's not to scale, I don't think. But from the diagram, we know that the smallest mass was drawn as the smallest sphere, and the biggest mass was drawn as the biggest sphere. This distance here is like roughly a half of that. So taking a look at this diagram, you would imagine that A is pulled more to the right than it is up. So it does make sense that this red force here to the right is an order of magnitude bigger than the force up. Putting those two forces together, you've got Fc on A and Fb on A that contribute to the net force on A. So we use Pythagorean theorem with those unrounded numbers to get our angled force, that hypotenuse. And then we use tan inverse to get the angle. And we get a net force of 4.3 times 10 to the 9 newtons, 7 degrees up from the right. Okay, so there's also the energy associated with that force. So the gravitational potential energy is Eg. It describes the energy stored when two objects with mass are held at a certain distance apart. Eg equals negative gmm over r. So notice now r is not squared. You don't have to memorize these equations, but when you're writing them quickly as you're doing problems, you want to notice these differences. Remember, I said when two things are confusingly similar, you want to write them side by side. Look at how were they similar and how were they different. Even though you're given a formula sheet, even though you have open book equations, you just don't want to accidentally write something incorrectly. So Fg was divided by r squared. The equation for g was divided by r squared, but Eg is not divided by r squared. Also notice this negative. So the negative indicates that the two objects are gravitationally bound to one another, and they would move one towards one another. If we released this, if we didn't prevent this rock from being held up here, it would want to crash down to the earth because it's gravitationally motivated to be there. Yeah. So we can also think of this equation as the work done to move an object from infinitely far away to a distance r from the mass. So from infinity to r is that's what this is. So if it was like a delta, it would be final minus initial. Well, it would be minus initial, but since you're dividing by infinity, it would be 0. So this can be thought of as the work done to move an object from infinity to r. Okay, now if we talk about orbits. So the moon is orbiting the Earth and the Earth is orbiting the sun. You've got all the planets orbiting the sun. There are many different natural satellite examples that you might see, questions that you might see. And we also have artificial satellites that are also orbiting planets. And so there's lots of different applications. So recall what we've just done is give a universal law of gravitation, and there is a gravitational force of attraction between any two objects. Satellites are objects that revolve around another body due to gravitational attraction. So we can have natural satellites like planets revolving around their sun or moons orbiting around their planet. We can also have artificial satellites. So examples are RadarSat-1, RadarSat-2, global positioning systems, the International Space Station, and these are all applications that you should read the brief description of in the textbook. So RadarSat-1 and 2 observe the Earth, monitor environmental changes, and monitor the planet's natural resources. It's commissioned by the Canadian Space Agency. So these examples are highlighted in your textbook from the perspective of Canadian contributions. We've got global positioning systems, and it's coordinated several satellite signals in order to determine the object's location of Earth within 15 meters of its position. And the process is called triangulation because it's 3 satellites that you look at the intersection of the range for 3. And that's also something to read about. Read the brief description in the textbook in order to answer one of the questions for homework. Okay, the International Space Station, which is very important. This is an example of an artificial satellite. It is a space station that is a spacecraft where people live and work. And it orbits the Earth at an altitude of about 300 to 400 kilometers. It supports many different research projects. It also studies human responses to space travel and microgravity environments. And just note that microgravity is present in free fall, but it's not the same as zero gravity, which only occurs if you are extremely far away from Earth. So we would say, quote, outer space. And again, like from the Canadian perspective, why do we, what is something to, I guess, be proud of is that a few years ago, so in 2013, I guess 7 years ago, a Canadian astronaut was the commander. So his name is Chris Hadfield. You've probably heard about him. And just a fun fact, Chris shot the first music video ever to be filmed in space in May 2013. So note gravitational field strength at 350 kilometers orbit, which is the height of the ISS, is 8.7 newtons per kilogram. So there is still a significant gravitational force at that altitude, and it's incorrect to say that astronauts that are on the ISS are in zero gravity. So why do they look like they're floating around? There's a few very helpful videos in visualizing this, and I've linked to them below. But it's just, I guess the bottom line is that microgravity does not equal zero gravity. A microgravity environment is present when any object is in free fall. So the astronaut is in free fall towards the Earth, and the satellite is also in free fall towards the Earth. And if an object is falling together with another object, so the astronaut relative to the satellite, does not look like there's acceleration. So from the frame of reference of inside the satellite, the astronaut is not accelerating to the ground of the satellite, which is why you don't sort of see that. Astronauts aboard the ISS are in constant state of free fall and are thus in a microgravity environment. The value of G at the altitude of the ISS is 8.7 newtons per kilogram. It's incorrect to say that astronauts are in zero gravity. So let's look at satellites in circular orbits. So I guess it's worth noting that many orbits that we kind of approximate as being perfectly circular are actually elliptical. But for any examples in this course, we're going to assume that they are perfectly circular to kind of simplify the problem. So this satellite, ISS, is actually in a circular orbit around the Earth because we can control it. I mean, I guess, except for the times where we're changing altitude to change what we're looking at. So let's look at the situation where you have the massive Earth and the relatively lower mass satellite away from the Earth. What if only the force of gravity was acting on this satellite? We would have the force, the attractive force of the Earth on the satellite, and we would have the attractive force of the satellite on the Earth. So we would have that action-reaction pair. Without sending this satellite at some velocity horizontally, or I guess in this case, up and down, without the orbital velocity, so if this had no fuel, the force of gravity would pull the satellite towards the center of the Earth. Now, if we only had orbital velocity, but the Earth wasn't there, without gravity, the satellite would fly off in the direction of the orbital velocity. So we have actually talked about this before, that if something is traveling in uniform circular motion, like a yo-yo, and if you suddenly cut that string, you see the tangential velocity more obviously. But what if you have both that velocity and the force? So if we have a net force towards the center of a circle and we are traveling in that, if we have a force that is 90 degrees to velocity, this is an example of centripetal acceleration. So every time that satellite wants to keep moving that way, as per law of inertia, objects in motion in a certain direction want to keep going in that motion. Every time that satellite wants to keep going in that direction, it is being pulled towards the center of the Earth. So this is how we get, recall that's how we get uniform circular motion. You wouldn't believe how long it took me to do that animation. So a satellite in a circular orbit around another body is an example of centripetal motion. Recall in chapter 3, this is a slide from chapter 3, we always had the velocity. Centripetal acceleration is responsible for the change in direction. And this happened because the centripetal acceleration and instantaneous velocity are 90 degrees, because acceleration is always towards the center of the circle and velocity is always tangential. So when there's 90 degrees between acceleration and velocity, and it's always that way, that's how we get circular motion. Recall that we have these equations for centripetal acceleration. So what causes the centripetal force in this case? In this case of orbits, we've got the force of gravity. Remember that the net force that causes the uniform circular motion is the centripetal force. We combine Newton's second law with the equations for centripetal acceleration and solve problems. The net force or centripetal force is directly towards the center of the circle. So we've got the centripetal force is equal to mv squared over r. So how does that relate to satellites? Well, for the satellite, at the point of the, any point of the orbit, the gravitational force equals the centripetal force, and then we can rearrange to solve for V. Notice how one of the masses cancels out. So you might wonder, well, which one is the mass that cancels out and what's left over? So this is the mass of the thing that is orbiting. And we've got the planet and the thing that's orbiting. So the thing that cancels out is the satellite mass, and we're left with the planet's mass. So our final equation here that we can use is the speed of the satellite, v, is equal to the square root of gm over r, where g is the universal gravitational constant, m is the mass of the central body, so I think of that as the mass of the planet, and r is the radius of the orbit. So that's from the center of the planet to the center of the satellite, not necessarily the radius of the, or not usually the radius of the planet. You'd have to be orbiting very low to the surface of the planet. So just be aware when solving these problems in your practice problems, there is a geosynchronous orbit, which means that the orbital period is 24 hours. Altitude refers to how high above the surface that you are. So you'll have to take the radius of the planet, which is the center to the surface, and then add the altitude, which is the surface to the orbit. Okay, one more example. So for example, hang on one second. I just want to make sure that when I've done that share, the volume is as good as it can get. We have the International Space Station orbiting the Earth, and this is on page 3 of the student notes package. So we've drawn a diagram, and let's label our givens. So in the question it says, well, the only question directly given in that question is that the Earth is at an altitude of 350 kilometers above Earth's surface. So that's worth noting. This is what we're given here, 350 kilometers. So before going to assign that a variable, let's just take a look at some of the equations that we've learned in this unit so far. So orbital, or problems where you have an orbit, it's an example of uniform circular motion. And it satisfies that criteria of acceleration being towards the center of the circle, because the acceleration is due to gravity, which is always, the gravity vector is always towards the center of the planet or the more massive object. And then velocity that is tangential to that acceleration. So you've got acceleration this way and velocity this way. So you have that 90 degrees between velocity and acceleration. We have uniform circular motion. In uniform circular motion problems, you draw a free body diagram, and then your F net is your centripetal force is your net force. And in this case, what is causing that? It is the FC is gravity. So the force of gravity. So you set your centripetal force equal to gravitational force, and you get, you would substitute mv squared over r equals capital GMM over r squared. Now, when we do that, setting one equal to the other, it's worth noting that there are a lot of m's. So what I usually do, instead of labeling M1 and M2, I usually use big M for the mass of the planet, or the bigger mass. So GMM over R squared. So just question, is this M and this M the same? Well, this is the mass of the object that is traveling in that uniform circular motion. And this is the mass of the planet. This is the mass of the satellite. So these two masses are referring to the same masses, and so they cancel out. V is the speed of the thing that is exhibiting a circular motion. So that's the speed of the satellite squared divided by radius equals the universal gravitational constant times the mass of the planet divided by r squared. What is r? So pause this video right now and really question, what is r? So r is the distance from the center of the Earth to the satellite. So we're not directly given the distance, the center to center distance of these two objects with mass. So what we're gonna wanna do here is in our given section, we're gonna wanna find what is the r that we are going to substitute it in. I guess if it doesn't even cancel out, and we will see that one of these r's this r cancels out with one of these r's. So one of the r's is left behind, and we are gonna need an r. So what is given? We are given 350 kilometers, but we also need to add the radius of the Earth from the center of the Earth to the surface. So in many cases we've done before, especially grade 11, the distance from the surface of the Earth to the object was near the surface of the Earth. It was an insignificant altitude compared to the radius of the Earth. But in grade 12, we're going to want to consider whether it is or it's not. It's often not insignificant. So the radius of the Earth is 6.38 times 10 to the 6 meters plus 350,000 meters. So just remembering that kilometers to meters, we multiplied by 1,000. So if we add those two together, that gives us the r that we'll substitute into the equation. And that is, oh, hello, cat. Okay. Goodbye, cat. The cat is, we'll have none of, oh, hello. Okay, let's move. 6.73 times 10 to the 6 meters. So we have r as a given. What else does not cancel here? So to clean that up, we have v equals gm over r. V squared. So that means if we don't want v squared, we have this as our equation. So this is our equation for the speed of the orbit. Sorry, I'm just gonna move my cat here for a second. Okay, so capital G is the universal gravitational constant. And we do have that value, 6.67 times 10 to the negative 11 newtons meters squared per kilogram squared. So I don't expect you to memorize that value or the units. It will be given to you. You will also be given the radius of the Earth. So you will be given the radius of the Earth, but it may not be given directly in the question. You'll need to know to look for it. So capital G and radius of the Earth, you'll need to know to look for it. So if this is our equation that we're going to use, we do need those values. So just double check that. Is there anything else that we do need? Well, we'll need the mass of the Earth. Is that in a table of values somewhere as well? And it is actually underneath my cat. So mass of the Earth, because I haven't memorized it either, 5.98 times 10 to the 24 kilograms. Okay, so we've got mass of the Earth, the center to center distance, which was the radius of the Earth plus the extra altitude. We've got universal gravitational constant. So we have everything we need to solve this problem using the equation that we came up with. So speed equals square root of g times mass of the Earth all of that divided by center to center distance, 6.73 times 10 to the 6 meters. So checking our units here. So with the unit analysis, I'm just changing colors here. So this 1 kilograms cancels with the second kilograms. One of these 2 meters cancels with this meters. And we're left with newtons meters per kilograms. So does that equal meters per second? So that's what we're questioning. Well, do you remember a newton? Because F net equals MA is the one that I always remember. A newton is a kilogram meters per second squared. So that times a meter divided by kilograms. So we've got the kilograms canceling out, and we've got meters squared over seconds squared. So actually that's what we want, because we want v squared. We're going to take the square root of it. So the units checks in, and we can just calculate on our calculator. Nine, 8 times 10 to the positive 3 meters per second. So I expect to get a really fast speed in the thousands. So I think one of the things that makes this unit difficult is there looks like there's not a lot of information in the question, and you have to go find your appropriate constants. And then the other thing is doing your common sense checks is a bit harder because we're working with really big numbers in the gravitational unit, and then maybe really small number in the electric unit, or the numbers are very large or very small orders of magnitude. So doing our common sense check will really require doing a lot of practice problems. So this passes my common sense check because I've done a lot of problems, but this number for my calculator is not rounded the appropriate sig figs. I checked the sig figs of every number that went into this calculation. So all of these numbers that I looked up were still measured numbers, but the number that was with the smallest number of sig figs was the 350. So we rounded to 7.7 times 10 to the 3 meters per second. And that's our answer for part A. For part B, and part A was, what is the speed needed to maintain its orbit? So if we're going to maintain the orbit, then the force of gravity is what makes up the centripetal force, which causes the uniform circular motion. So that's why this speed is the speed that is needed for maintaining the orbit. Part B says, what is the orbital period of the ISS in minutes? So this is for part A. For part B, period is the time, and what we've just calculated is the speed. Speed is equal to total distance over total time. And if we can say that the distance in the numerator is traveling around once, then the time we're referring to is the period. So the period of orbit is equal to the distance around once divided by that speed. The distance around once is the circumference of a circle, which is 2 pi r. And then, do we have everything in order to solve? We have r, we have v, so we just substitute the numbers in. So t equals 2 times pi times 6.73 times 10 to the 6 meters. Again, make sure you don't just simply sub in 350 kilometers, and make sure you don't sub in just the radius of the Earth. divided by, now it's unavoidable that we're going to have to carry forward the answer, but we're going to carry forward the unrounded answer. I hope you can still see this. This marker is not as fine as it used to be. So 2 times pi times 6.73 times 10 to the 6 equals, divided by, actually I'm going to use answer button. I really hope you guys are using your scientific notation buttons. So EE or EXP, email me if you have no idea what I'm talking about, because since we're working with very large and very small values in this unit, you really want to know how to do calculations with scientific notation on your calculator. So you get 5 4, oh, you know what? I'm going to calculate this in seconds, which is kind of useless. Does it specify what unit of time? You know what? It doesn't specify the unit of time, so it would be fine to round this to 2 sig figs per second. If you want to know what that is in minutes, we're going to divide by 60. That would be equal to 92 minutes. So you can report it in seconds or minutes. I think probably the best answer will be reporting in seconds, because that's SI units, and if it's not specified, it's always safer to report in SI units. So that's the example where the International Space Station is orbiting Earth. Okay, so now it's time for some practice questions. It looks like more than it is, because there are some conceptual questions which might not take as long as a calculation question, definitely not as long as that example. So once you do the practice questions, make sure you submit to Google Classroom. Make sure you complete the exit ticket to prove that you watched this video to some extent at least. And have a great day. Be safe, be well.